My name is Christopher Lusig, and this is my video lab report on Lab 4, Oscillations. For this lab, I developed the following problem statement: how to model the physics of extreme sports with ropes using the physics of oscillating motion of a mass on a spring. The answer to this problem is important because it will help us to better understand oscillations, physics principles, and physics in everyday life. To complete this lab, I used Newton's second law, Hooke's law, the energy principle, tracker, and GlowScript. The following physics principles were used to complete this lab. I input these formulas into GlowScript in order to create a computational model for this situation. The forces acting on the mass are the force of gravity and the spring force. Also, kinetic energy, gravitational potential energy, and spring potential energies make up the total energy of the system. Their formulas are shown here and were used in the code. My procedures for this lab were to download the video of the oscillating motion of the mass on a spring, analyze it using Tracker, then download the Lab 4 starter code, and then create a computational model by inputting correct formulas into the code. I then used this to compare the predicted and observed data. Here is the original video of the oscillating motion. Using Tracker, I track the position of the mass over time as it continues in oscillating motion. This produced position versus time graphs and data points shown here. I then downloaded this data for comparison with the upcoming computational model. I then created a computational model using the Lab 4 starter code. I input the mass of the ball, properties of the spring, and formulas for energy and forces. These inputs will allow the code to run. When I hit run and input the file for my observed data, the computational model runs and plots energy and position graphs as shown. The position graphs compare the experimental data to the model data, shown here. As you can see in this graph, total energy is constant while delta K, delta U for the spring, and delta U for the gravity oscillate throughout the motion. This is due to the changing position of the mass on the spring. Here you can see the difference between the computational model and the observed data. These graphs are slightly different due to the small human error and the fact that the computational model does not account for drag or friction. This causes the position versus time graphs to be slightly different. These points lead to my improvements. A drag component could be added to the code to make the computational model more accurate to the real situation. This would make the graphs line up better. In addition, a device could be used to drop the mass to ensure it begins at rest with zero initial velocity. This can make it even more accurate. This model and explanation can be used to better understand the experiment. As shown to the right, the force of the spring acts upwards while the force of gravity acts downwards. The force of gravity is always in the same direction with the same magnitude because the weight of the mass does not change. However, the force of the spring changes based on how far the spring is stretched or compressed. The difference between the relaxed length, L0, and the instantaneous length of the spring changes the magnitude of the spring force. This means that the spring force is greatest in magnitude when stretched or compressed to the maximum. In addition, the total energy will stay constant as the surroundings have no interaction with the system. This means that delta E is zero. However, kinetic energy and potential energies will vary over time, as shown in the graph here. Delta U gravity and delta U the spring all vary over time as the kinetic energy also varies. However, delta E stays constant throughout the graph. I then answer, what does it mean? The energy principle is satisfied because the change in total energy, delta E, is zero. This is because the system is closed and it means that the surroundings have no interaction with the system. This is also shown in the graph to the right. I could also use the data to calculate the periods in the x and y directions. For 4 oscillations in the x direction over 6.571 seconds, the period is 1.643 seconds. For 5 oscillations in the y direction over 7.619 seconds, the period is 1.524 seconds. I calculated this by finding the difference in time over full oscillations in the graphs as they return to minimum points. I then divided this time by the number of oscillations to find the period. In conclusion, I was able to use Hooke's law, Newton's second law, and the energy principle for this lab. The predicted motion is slightly different from the observed motion due to drag, friction, and human error. This can be seen through the different Tracker and GlowScript data. This concludes my video lab report. Thank you.